Okay, today what we're going to learn about is the absolute value function. So our goals are what is the absolute value function and how do we graph it. And this covers the integrated algebra standard AG4. It covers part of it where we have to identify and graph the absolute value function. Our vocabulary is function and absolute value. Okay, so first of all, let's talk about the absolute value function, which is this function right here, y equals the absolute value of x. Now, if you recall, what the absolute value does is it takes the distance between a number and the number 0. So, for instance, the absolute value of 10 is equal to the distance that negative 10 is away from 0, which is positive 10. So the absolute value of negative 10 is positive 10. The absolute value of negative 8 is 8. Of the absolute value of negative 6 is 6, and so on. So we can go ahead and fill in this chart. And then when it's positive, like the absolute value of 2, well, the number 2 is just 2 units away from 0. So it keeps everything that's positive, it keeps it as positive. So we can fill in the rest of the table here. Now, if I graph these points on the xy plane, I would get, so the first point would be I can get the origin. Now, going in this direction, we have the x value of negative 10 arrives at a y value of positive 10. Negative 8 arrives at negative 8. Oops. Okay, and I just went ahead and plotted the rest of the points here. Now, what you're going to see is if you connect these points, you get this v. Okay? So this is what the absolute value function looks like, and it actually drops down to the origin, and then it starts coming back up. Okay? Now, if you look at the graph, the table rather, you'll see what happens here. So the higher the negative number is for x, the higher the positive number is as an output for y. So it does that, so it keeps decreasing until it gets to 0, and then it starts increasing again. So the absolute value can be seen as a composition of two different functions. The function y is equal to negative x. Okay, that's this branch right here. And the function y is equal to positive x. And that's this branch right here. Okay. Now the reason why it's like the composition of two functions is because the line right here, y is equal to negative x, would look like this, right? It goes to the origin, has a slope of negative 1, so that's what it would really look like in mx plus b form. And the graph y equals positive x would look like this. Y equals 1x plus 0, where it has a slope of 1 and also goes to the origin. Now the absolute value function is, the absolute value function is this green function. So let me take off what I've done. The absolute value is this green function, so it takes part of the graph of y equals negative x and part of the graph y equals x and sort of splices them together. Okay, we need to remember this as we go through because we're going to start changing some numbers in here and see what the function does when we change the numbers. So the first thing that we're going to try to change is we're going to subtract a constant from x before we take the absolute value. So what I've done here is I've made a table of values. I've kept the x values the same. I've put the y values for the standard function, y is equal to the absolute value of x. And I want to investigate what happens when I take away 4 before I take the absolute value away and take away 4 after I take the absolute value. So first of all, let's look at this one right here. So this function is saying take the y is equal to negative 10 minus 4, and then, or the absolute value of negative 10 minus 4. So y is equal to the absolute value of negative 14 or positive 14. So this gets 14. Okay, for negative 8, y is equal to the absolute value of negative 8 minus 4, which is the absolute value of negative 12, which is positive 12. Okay, so negative 6 is going to be the same. Negative 6 minus 4 is negative 10. The absolute value of negative 10 is 10. So you can see that every time I change this by 2, this one goes down by 2. So let's continue using that to fill in the rest of our table here. Okay, and then when it gets to 0, so when I put x in for 4, or 4 in for x rather, I get 4 minus 0, which is 0, and then absolute value of 0 is 0, and then it starts going back up. Once it's bounced down to 0, it starts going straight back up again. Okay, it looks like the branches are a reflection of each other. So going back here, the branches are a reflection of each other. Right now in the original, it's reflected over the y-axis, but we'll see in the next one, there's a different line of symmetry. So if we start plotting these points right here, okay, we'd have negative 10, 14, which is off of our graph. I'm going to go down, I'm going to plot negative 6, 10, because that's the first one on here. Negative 6, positive 10 is here. Negative 4, positive 4, or sorry, negative 4, positive 8 is right here, and so on. Okay, now I've plotted the left branch here. So I've gone and plotted at 0, this is 4. I've plotted the left branch. So if you can see it comes and drops down. Now it starts being a reflection. So this is like the line of symmetry is x is equal to 4 right here. And so it starts going up in the same manner in which it went down. Okay, so it still has, it's sort of, the branches still look alike. And remember, the absolute value function, the standard one, I'll plot this in red, looks like this. Okay, and so the green one is your new one. And so all you've really done is you've taken the absolute value function and you've shifted it to the right by 4 units. Now it's a little counterintuitive because it looks like if we subtract 4 from the x, we would shift it to the left 4. But in fact, what happens is it's taking all of these original values and it's shifting it down. So like this 8 was achieved by so the original function gets 8 when you put an x of negative 8 in there. But the new function, this function that we're looking at here, gets 8 when you put in negative 4. Okay, well, what's the difference between negative 8 and negative 4? Negative 4 is 4 units to the right of 8. Okay, again, look at what happens when we used to get a y value of 0 when we put in an x value of 0. Now we get a y value of 0 when we put in an x value of 4. 4 is 4 units to the right of 0. Okay, so what ends up happening is when you take something away, it shifts the whole graph to the right. So where it used to drop down is at the origin. Now where it drops down is 4 units to the right. So if I take the origin and I do 4 units to the right, that would be 4, 0, and that's what we see here. Okay, that's the vertex of this absolute value function. Okay, now let's investigate what happens when we take 4 away from it after we take the absolute value. So here, in this column right here, we take the absolute value of negative 10, which is 10, then we subtract 4, which is 6. And then we have so essentially what we can do is we can take the column, the second column here, and we can just take 4 away from that because that's already, the absolute value is already taken. So 8 minus 4 is 4, 6 minus 4 is 2, 4 minus 4 is 0, 2 minus 4 is negative 2. 0 minus 4 is negative 4. 2 minus 4 is negative 2. Okay. 4 minus 4 is 0. 6 minus 4 is 2. 8 minus 4 is 4. And 10 minus 4 is 6. So if I plot these, okay, just to be clear what I'm plotting these values right here and these values right here. So those are my x, y combinations, okay? So I'm plotting negative 10, positive 6. So negative 10, positive 6 would be there. Then I'm plotting negative 8, positive 4. Okay. Then I'm plotting negative 6, positive 2. Then negative 4, 0. Okay, so you can see this starts my left branch right here. But I continue beyond that because I go to negative 2, negative 2, negative 2, right here. Then 0, negative 4, so it actually has, your vertex starts going down like this. And then after you go to negative 4, that's the minimum value, that's the min for this graph. Then I start going back up again. I go to 2, positive 2, negative 2, which is, oops, this should have gone down to negative 4 right there. then positive 2, negative 2 was right there, and then 4, 0, so 4 zeros here. Okay, what ends up happening is my branch continues going up. So let's compare the red plot, the original plot of y equals the absolute value of x, to this blue plot, and what you see is it's been shifted down 4. Okay, so this goes down by 4 right here. So for instance, let's just compare these. Let's compare these. So this right here was a shift right by 4, okay, and this was a shift down by 4. So it turns out if you subtract or add something to the x value before it goes to the absolute value, that affects the horizontal position. If you subtract or add something to the value after it's gone through the absolute value function, that shifts its vertical position, okay? And we can look at the table of functions here and see what happens is what we're doing so after we get the absolute value, which is in this row right here, in this column right here, we take 4 away from it. So we're literally from here to here, it's shifted 4 down. Okay, so the y value shifts 4 down. 8 shifts 4 down to 4, 6 shifts 4 down to 2, and so on. So the general rule here is when you add something inside the absolute value function, it shifts to the right or left. So when you add it, this is going to shift left by the value c, by the constant c, and this is going to shift right by the constant c. This is going to shift up by c, and this is going to shift down by c. Now again, it's sort of the vertical changes are more intuitive, right? If we add something to it, it makes sense that it would go up. If we subtract, it makes some sense that it would go down. But the horizontal changes, if you add or subtract something before you take the absolute value, those are a little bit more counterintuitive because you would assume that they would work in the opposite direction. But what you need to remember is that when you're adding something to x before you take the absolute value, what ends up happening is that it achieves all of its y values before it used to achieve those y values. So for instance, the absolute value function it's centered, or the vertex is at the origin, but if you add something to x before, it achieves that min value before, in x values before it used to. Okay, so this is the change right there. So let me put that in red. This right here is the change when you add to it. Now let me put this in green here. If you subtract from it, what ends up happening is it shifts it to the right. Okay, and the same goes for here. Not the same, it's the opposite way here. If you add something after the absolute value, it shifts up by c. And if you subtract something here, it shifts down by c. Okay, it's the same v, but it just shifts left, right, up, or down. Okay, let's investigate when we multiply a number by the x value here. So if I multiply the number -2 to the x value, so again, what I've done is I've taken the same x values and I've put the y values for the standard function in so that we can compare them. I'm going to go ahead and pause the video and fill in this table, and you can do the same here. So we're going to investigate this one first and then the one to the right. So over here, I'll do one of the problems for you. -2 times -10 ends up being +20, but the absolute value of +20 is just 20. Okay, so I filled in the table here, and so what you see is that it's doing the same pattern as before. It's decreasing steadily by 4s this time, not by 2s. Well, it's decreasing by 4s because I've decreased the x by 2 every time. So really the slope is -2 here. Okay, so it's going down by 2s, and then it starts going up the slope here is 2, because again, I'm increasing the x value by 2, and the change of the y value is 4, so that's a slope of 2. So what ends up happening is when you plot these points, you get the lines y equals -2x, and the lines, so this is the line y equals -2x, and this is the line y equals 2x. Okay? So let's plot these points real quick. Okay, so I plotted the points starting from -4 to +8 and downward. So what happens is you have the same basic shape, the basic V, but it's going up a lot faster, right? Because the slope of this branch of the line right here is y, this is the equation, y equals -2x, and the equation of this branch is y equals 2x. So what happens is it ends up changing the width of the funnel, or the width of the V. It goes up a lot faster than it did before. Now, just in the interest of time, I'm going to fill in the next table. The next value here we're going to investigate is what happens if you multiply by -2 outside the parentheses. Okay, and so actually what we're going to just do is take the values, let's take the values of y equals the absolute value of x, so these values right here, and just multiply them by -2. So you'd end up getting -20, -16, nope, you'd end up actually getting, oh, no, that's right, -20, -16, -12, -8, -4, 0, -4, -8, -12, -16, and -20. And so what that looks like when you plot it is it looks like the same as this purple V, except everything has been reflected. Like, look at all the x values remain the same, but all the y values change. And so remember what that is from our geometry unit. If all the x values stay the same and all the y values change, it's a reflection over the x-axis. Okay, so what happens is if you multiply it by a negative number on the outside, it reflects it. It's like two different changes happening. It changes the 2 there, changes the width of the funnel, so it makes it go down faster. And the negative reflects it over the x-axis. Okay, oops, that's the same slide. So if I investigated this one further, this is a positive number. I did the same thing, but just with a positive number. What would end up happening is this column that I would fill in here is, it would be 3 times the, so I'd multiply x by 3 to get -30, and then I'd take the absolute value of -30 to get 30. So this ends up being like 3 times what these values are. So this is 30, 24, 18, 12, 6, 0, 6, 12, 18, 24, and 30. So this is 24. So it ends up going up a lot faster, 3 times faster, in fact. So this would be 0, and then at 2, it's already at 6 right here. So this is this graph right here. This is a y equals the absolute value, 3 times the absolute value. The absolute value of 3 times x. And if you take the 3 out, you end up, okay, so if you take the 3 outside the absolute value, it actually doesn't really make a difference. So to figure this out, you take all the absolute values of x and multiply it by 3. So again, you get 30, 24, you get the same thing as you just did. Okay, so it doesn't matter if the constant is inside, so this is the graph of this one right here. If the constant is positive, it doesn't matter if it's inside or outside, it makes the same change. Okay, now if it's a fraction, it does something a little different. So if it's a fraction, imagine what this function is asking. It's asking you to take all the values that you got for absolute value of x, and it asks you to divide them by 2 or multiply them by 1/2. So it takes 10 and it goes to half of that, which is 5, 4, 3, 2, 1, 0, 3, 4, 5. And so it takes so here, I'm going to draw the absolute value function. Let's see, this is the original absolute value function. And it would go -5, -5. So this is this function right here, y equals the absolute value of x. And this new one, it makes the v wider. So at 0 is still 0, but then at 2 you have 1. So you go to 2 and you go to 1 right here. And then at 6 you have 3 right here. So this is the branch right here, and the right branch would do the same. Okay, so this is like the function y equals 1/2 x, and y equals negative 1/2 x. So when you have a number outside here that is a fraction, it makes the funnel wider. So just as a general rule, if case 1, if your c value here is negative, it reflects it over the x-axis. If your c value is between 0 and 1, it makes the v, it makes the v wider. And if your c is greater than 1, it makes the v more narrow, because it's going up faster. So the slope of the line is going up the slope of the two lines that make up the absolute value function are decreasing faster and increasing faster, so it makes the v more narrow. Whereas if it's a fraction, a proper fraction, it makes the v wider because it's not going up as fast, nor is it decreasing as fast. Okay, so we can take all these ideas together and we can graph these functions based on what we know about transformations. So here, I know the first transformation it's going to go through is it's going to shift to the left 4, and then this 2 is going to make it go the v more narrow. Okay, so let's think about what the origin would. So the vertex is normally at the point 0, 0. So if the vertex shifts to the left 4, the vertex would be at 0, or negative 4, 0, rather. So vertex is negative 4, 0. So the first thing I do is I plot the vertex. So plot vertex first. So it's at negative 4, 0. And then the slope of the line, the slope of the lines are going to be y is equal to 2x, and y is equal to negative 2x. Those are my two branches. So y is equal to 2x means I go up 2 and right 1, up 2 and right 1, and this gets me my branch right here. And then I go up 2 and left 1, up 2 and left 1, and there's the branch of my other one. And that is this graph. This is the graph of the function y equals 2 times the absolute value of x plus 4. Okay, now the next one, y equals the absolute value of x minus 4. So remember the constant's on the outside, so we shift down by 2. So let's look at what happens with the vertex. Let's plot the vertex first. Shifts down by 2, so that means that the y value decreases by 2. So the vertex is going to be at 0, negative 2. Now there's nothing being multiplied on the inside or the outside for x, so the slopes, the lines that make up the branches is just y is equal to x, and y is equal to negative x. So it's going to have a slope of 1, so it's going to go up 1, right 1, and so on. And then up 1, left 1, up 1, left 1, and so there's your branch. So that's y equals absolute value of x minus 2. Okay. Now here I have two changes that I have to make. So the first change I make, if I do this in order of PEMDAS, is I take the absolute value of x and I'd multiply it by this number out here. So remember, this is like negative 1 times the absolute value of x, and then I subtract 2. So this is a reflection over the x-axis. And then I want to decrease that by 2. So decrease by 2. So if I plot the vertex first, if I reflect the point 0, 0 over the x-axis, it actually just becomes 0, 0. And then if I transfer it down by 2, it becomes 0, negative 2. So let's plot that first. There's 0, negative 2. Now to make the branches, think about the slope of this line. Okay, the slope is, the branches are the slope y equals negative x and y equals x. So here the slope is going down 1, right 1, so it goes down like this. And here the slope is going down 1, left 1, so it goes down like that. So if you think about it, that's exactly what you would expect it to be. You took the graph, so the graph of y equals negative x would look like this. Okay, that's the graph of the function y equals, the graph of the function negative, or the opposite of the absolute value of x, that's this red one, and you shifted it down by 2. Okay? All right, we'll do one more. So let's think about this one. This one is, let's do it in order of PEMDAS. So the first thing we do is we add 4. That shifts it left by 4. And then we have an outside vertical shift of down by 2. So down 2. So think of your vertex. Your vertex 0, 0 goes left 4, which gets you negative 4, 0, because that shifts it on the x. And then down by 2 shifts it to negative 4, negative 2. So your vertex is negative 4 and negative 2 right here. Now think about the slopes of your branches. It's opening upward because there's no negative being multiplied on the outside, right? There's no negative on the outside. And the slope of your line is just going to be 1 because you have, again, you have these lines y is equal to, well, the slope anyhow is going to be 1. So you go up 1, right 1, up 1, right 1 from your vertex, and there's your right branch. And left 1, right 1, left 1, right 1 here. And so this is the graph line y is equal to x plus 4 minus 2. And that's the last one we're going to do today. So we looked at what these changes do, right? The first thing we looked at was what the graph of y equals the absolute value of x looks like. And then we looked at how we can change it and shift it using our ideas of transformations, like mainly translation and dilation, in order to figure out a whole bunch of functions. So not only y equals the absolute value of x, but all these functions that have some sort of vertical, horizontal, or dilation change to them.